Hey y'all, we are Memphis Kim University and we're back for another Calculus Done Wrong lesson where we wrong calculus before calculus wrongs us. And today we're going to be continuing our differential equation unit on the AP exam and we're going to be talking about Euler's method. So Euler's method, as of the making of this video, is only found on the BC portion of the AP exam and it's not found on the AB portion of the AP exam. But keep in mind that even if it is only a BC only topic, it is not actually a hard topic. It is easier, in my opinion, than some of the AB counterparts. So because we're doing calculus wrong, what we're going to do is we're just going to focus on the method itself, the formula that corresponds to the method, and then we're just going to do examples. We aren't going to talk about the theory too much because that's calculus done right, but let me talk about it just a little bit so that we have an idea of what we're trying to attempt. So basically what's going to happen is we're going to have an equation of a line, and what's going to happen is the line slope is going to be the differential equation, some given differential equation. And what we're going to do is we're going to use the given differential equation and a given point to find and approximate y values of nearby x values. So for example, we're going to start off at something like 1, 2. And then what we're going to do is we're going to use a slope or a differential equation to approximate y values of nearby x values, so like 1.5. Then we're going to approximate the value of 2 using our approximation of 1.5. Then we're going to approximate the value of 2.5 using our approximation of 2. What we're going to be doing is the same thing over and over and over again. So it's a step-by-step process where you do the same step over and over again and you use the previous step to do the next step. All of this is very convoluted and all of this is very complex. So again, let's just go for the method. So this is Euler's method. Euler's method. And how Euler's method works is that there's going to be 3 main givens. So our 3 main givens are going to be a differential equation. So dy dx is equal to some differential equation. This is to denote that usually our differential equation is going to have 2 variables. So it's going to be something like y over x or 2x plus y or something like that. Then we're going to have a slope, a step size. So we're going to write h as step size. And then we're going to have an initial point. So keep in mind that our step size is basically the difference in between our x's. So again, we're going to start off at something like 2, 5. And then our step size is going to be given, so it's going to be something that's small because we're not going to be able to approximate far away x values. We're only going to be able to approximate nearby x values. So if we start off at our point 2, 5, and our step size is, for example, a quarter, what we're going to do is we're going to find and approximate the value of 2.25, then 2.5, and then 2.75. Using this point and this equation. So what's the equation itself? What's the formula itself that applies to Euler's method? Well, it's going to be yn equals y to the n minus 1 plus step size. So step size, well, we're going to use h though because we have a variable for that, times f of xn minus 1, yn minus 1. So this formula looks probably pretty intimidating, but keep in mind that this is our old friend actually, just the equation of the slope of a line. Because if you bring over the yn minus 1 and you divide by h, keeping in mind that h again is the difference between our x's and it's always equal. So it's like 0.25 because we're separating 2, 2.5, 2.5, 2.25, 2.5, and 2.75. So keep in mind that h again is the difference of the x's. So when you subtract over yn minus 1 and divide by h, you're just going to be left with y2 minus y1 over x2 minus x1 equals the slope. And that's the equation of a line, of course. This formula still might be kind of intimidating, so sometimes my students like me to write it in English. So in English, it's the new y equals the previous y plus the step size. And then what you're going to do is you're going to plug in, so this is really the method itself, the previous x and y into your differential equation. So again, this is a line by line thing where any time you're on a current line, you're going to be using the previous line. So the previous line or the line right above it will have an y and an x. So these are what I mean by the previous y and the previous x. So what you're going to do is you're going to take your previous y, whatever it is, and you're just going to apply this formula. So why don't you pause the video and why don't you write down this formula, whether you want to write the math way or the English way. And again, these formulas are complex to look at, but they're actually easy to apply. So I just want to go for examples. So write down this formula. I'm not going to talk about write down this formula again probably because we have to do too many things and I don't have enough space on this tiny little board, but I'm going to say the formula over and over and over again. New y equals previous y plus step size, plug in the previous x and the previous y into your differential equation. So let's get started. Let's do some examples. So again, hopefully you had the opportunity to write out this formula. So in this case, what we're going to do is we're going to actually have givens here. So let's start off with this given. So again, all of these things are given, so you don't have to come up with any of this stuff. So we're going to have y over x. Our step size is going to be 0.25. And then finally, we're going to have the point 2 comma 8. Then we're going to, the question will be approximate f of 2.5, where f of x equals y is this solution to the differential equation. So one of the main errors that I'm trying to avoid that sometimes my students make is that because they're so excited to do Euler's method, they'll do the process too many times, or they're too intimidated by Euler's method, so they do the process too few times. But what happens is, if you write out the way, the process in terms of the way I like to write it, line by line by line, then it should be good to go. You shouldn't be able to mess up how many times to do it because it will be very obvious how many times to do it. So what I like to do is I like to write out the given point first off. I like to write out x is equal to 2 and y is equal to 8 because this will be the previous x and the previous y for my next line. So then keep in mind that because we have a step size of 0.25 and we're starting out at x equals 2, I'm not going to be able to jump from 2 to the number I want, 2.5. I have to stop midway. So you have your 2, and you're going to approximate 2.25, and then finally after that, you're going to approximate 2.5. What you do is you take your initial x and you just keep adding your step size. So in this case, we're going to do x is equal to 2.25 first. So now we're going to do the method. So how exciting we're doing the method now. So again, the method is the previous y plus the step size, and you plug in the old x and the old y, or the previous x and the previous y, into this differential equation. So let's do that. So what's the previous y? Again, when I talk about previous, I'm talking about the line immediately above this one. So it's going to be 8, that's the previous y, plus the step size. Keep in mind that you have a choice of working with decimals or fractions, but I like fractions more. So I'm going to write this as 1/4. And then what's going to happen is you're going to plug in the previous y and the previous x into this right here. So notice that's going to be 8 over 2. So we don't need this many parentheses. It's going to be 8 over 2. And then you're just going to compute this. So this is going to be, this cancels obviously pretty nice. 8 over 2 is 4. 4 over 4 is 1. So this is going to be 1 plus 8, which is 9. But again, how did I find all these numbers? It's the previous y plus the step size, 0.25. And then you plug in the previous x, the previous y into your differential equation. So let's do this again. So it's going to be x is equal to 2.5. And again, we started off at 2 comma 8. We applied Euler's method to approximate the function at 2.25. Then we're going to do it again to approximate the value of 2.5 using this previous line. So it's going to be y is equal. It's still the same formula over and over again. It's the previous y and the previous x. But again, you just look at the line immediately above it. So I'm not going to be looking at 2 and 8. I'm going to be looking at this second line to find the third line. So it's the previous y, so it's going to be 9 plus the step size. And then what you're going to do is you're going to plug in the previous x and the previous y into your slope. So it's going to be 9. And because I like fractions more, keep in mind that 2.25 is the same thing as 9/4. So I'm going to write it as 9/4. And all we have to do is sort of simplify this equation. So that's what we'll do eventually. But again, hopefully you see where I got all my numbers. So it's the previous y plus the step size. So that's why this is always the same, because the step size stays the same in every single question. So it's going to be plus h, that was given. I read it as a fraction. And then finally, you plug in your previous x, your previous y into this. So that's why it's 9 over 9/4. Of course, you have to deal with fractions, unfortunately. In my opinion, that's the hardest part about these questions. But just be careful with fractions, right? So it's 9 plus 1/4, for example. And when you're dividing by a fraction, we're going to multiply by the reciprocal. So in this case, it's going to be times 9 times 4/9. But it looks like everything is canceling very nicely. The 9s cancel and also the 4s cancel. So you're going to be left with 1 again. So it should be 9 plus 1, which is 10. So that's how you do Euler's method. Again, you take a line and you look at the previous line and you do the formula previous y, so that was the previous y, plus the step size, plug in the old x and the old y into your differential equation. And that's all it is. You do this as many times as you need. So in this case, we did it 2 times because we have 2, 2.25, 2.5, where everything is separated by 0.25 because that's the step size. And then you compute these with fractions. I think it's easier than taking derivatives because the derivative is already given. It's easier than integrals. All it is adding and multiplying numbers, and you just have to know which ones to do and be careful of fractions. So let's keep doing a few more examples just to get the method down. So I'm going to erase this. Sometimes they don't tell you what the step size is, but they tell you how many step sizes. So in this case, we're going to have 2 step sizes. So we're going to have 2 step sizes. Then we are going to have the differential equation in this case, which again is given as 2x plus y. And then we're going to start off at the point, let's say 2 comma, let's not use 2 because we used 2 last time. Let's do 4 comma 1 or something like that. Shouldn't be too crazy. And then what we're going to do is we're going to try to approximate f of 5, where y is equal to f of x, just like normal. So in this question, it's slightly harder because we don't know this how big each step size is, but hopefully you can tell how big the step size is. If you need to, what you do is you take your number, subtract off your previous or the initial x, and then divide by the number of step sizes. But hopefully you know that to go from 4 to 5 and you have 2 equal parts, you're going to do 4, 4.5, and 5. And just like the previous one, we're using our 4 to find the 4.5, and we'll use our 4.5 to find the 5 value. We can't jump from 4 to 5, unfortunately. So in this case, we do have to note that h again is 0.5, but that's because 4 plus 0.5 plus another 0.5, 2 step sizes will be the x value that you want. So let's start with the process again. So again, I like to, in my first line, write out the initial. Sometimes my students don't do this, but then they're more likely to do it too many times because it's previous to go for the next one. So it's just a nice, easy thing to do. Then you're going to write your next x value, which it looks like in this case, it's going to be adding a 0.5, so it's going to be 4.5. And then we're going to apply the method. And again, the method is previous y plus step size, which is h. Then you plug in your previous x and your previous y into your differential equation, which is given. So in this case, it's the previous y, which is 1. Then the step size. Again, I like to work with fractions, so I'm going to write it as 1/2. And then what we're going to do is we're going to plug in the previous x and the previous y into this guy right here. So it looks like we're going to have fractions, but we're not going to be too scared of them. Previous x is going to be 4 times, we can just write it out. So plugging in 4 into this, plugging in 1 into this. We do have to simplify this, so it's going to be 1 plus 1/2. 8 plus 1 is 9. So it's going to be 9 halves plus 1. Well, 1 is just 2 halves, so it looks like we're going to have 11 halves here. But again, this is only the first line of Euler's method. We're going to have to do this method again. So it's going to be x is equal to 5. But the new previous x and the previous y is always the line immediately above it. So the formula again is previous y, so it's 11 halves plus the step size. So that's why this doesn't change from the previous line, because the step size is always the same, 0.5. So it's always plus 1/2 plus 1/2. And then what you do is you plug in the previous x and the previous y into your slope. So in this case, we're going to plug in 4.5 and we're going to plug in 11 halves. Again, I'm going to write everything as fractions. So 4.5 is 9 halves. So it's going to be 2 times 9 halves plus 11 halves. And unfortunately, we do have to work with a little bit of fractions, but it shouldn't be too crazy, I believe. So I'm not going to actually multiply this out because I already have a common denominator here. So it looks like it's 18 plus 11. 18 plus 11, do I know that math? Let's do this math on the side. So we have this 11 halves here, plus 1/2. If I had more space on this small board, I would do it immediately below it. But 18 plus 11, I believe, is 29. So it can be 29 halves. So it looks like our common denominator here should be fourths. Again, fractions are kind of annoying, but this is 22 fourths. plus 29/4. And then what is this? Well, it looks like we're going to have 40 plus 11, so this is the final answer is going to be 51/4. But don't focus too much on the fractions. Hopefully you're getting the method down. Again, it's the previous y, so in this case 1 plus the step size, plug in the previous x and the previous y into your slope, and just keep doing that until you have the correct number of times you need. So in this case it was 2 times, because we're starting at 4, going to 0.5, and then 0.5, and that's how it works. So even if the fractions get pretty intimidating, it's still the same formula over and over and over again. Previous y plus step size, plug in your previous x, which is 9/2, previous y, into your slope. So that's why it was 2 plus 9/2 plus 11/2. Just be careful with fractions. I might not have done fractions even correctly, but it's the least important step. Just having the method down pat is the better step, more important part of the process. Can't talk anymore. But let's do another one. We might as well keep practicing. So let's erase this and let's see some variations of this process, even if we're using the same formula. So in this case, what I'm going to do is I'm going to have 2x minus y, I think in this case. Let's actually have 2x minus 2y. Then we are going to have 1.5 as my initial x. And we are going to have something like 4 as my initial y. We're going to have 3 step sizes. So again, everything above here is our given stuff. Then this is going to be the question, f of 0. And then we're going to try to do this. So just like the previous one, in this case, h is not given, but hopefully you can tell how do you go from 1.5 to 0 in 3 different parts. Well, what we're going to do is we're going to subtract off a half each time. Because if you go 1.5, then 1, then 0.5, you always hit 0 after that third time. Keep in mind that in this question, h is actually going to be negative, so it's going to be negative 0.5. Because we are approximating an x value that's less than our initial x value. In the previous 2 questions, what we did is we approximated an x value that was more than our given x value, so we were having positive h's because we were adding the h every single time. In this case, we're subtracting the h. So just be careful that sometimes h is negative. But once we have this information, we should be good to go. We should be able to go for the question. So again, let's just do the process over and over and over again. If you want, why don't you pause the video? I won't watch you do work, and why don't you try to do Euler's method, 3 Euler's method it looks like, because we have 3 step sizes. Try to do it yourself. Be careful with those fractions. Previous y plus the step size, plug in the previous x and y into your slope. Try to do that. Again, I'll give you some time. Pause the video, and then 5 seconds, unpause it, and we will be able to sort of check our work and see if we got the same answer. So 5, 4, 3, 2, 1, let's get started. So again, what I like to do is I like to write out my initial thing. X is equal to 1.5, y is equal to 4, and then let's go for the formula. So in this case, the next one will be x is equal to 1. Remember, I'm subtracting each time because I want to go down to 0, but it's the previous y, so in this case, it's 4 plus, and you plug in the previous x and the previous y into your slope. So in this case, it's going to be 2 times 1.5 minus 2 times 4. So this shouldn't be too bad. Again, previous x, previous y into your slope. Keep in mind that we forgot the step size, so that's very important. So it's going to be minus 1/2. Keep in mind, why is it minus? Well, again, the h is negative, so usually it's plus h, but h is negative here, so it's negative 1/2. So let's try to compute this. So it's going to be 4 minus 1/2, and then this looks like it's 3, because 1.5 times 2 is 3. 3 minus 8 is negative 5, so it's going to be negative 5. So it looks like my final answer is going to be 4 plus 5/2. Well, 4 is 8/2, so it looks like we're going to have 13/2 here, which doesn't bode well for the question, but let's keep going. But again, we're just going to do it again, so let's leave some more space this time. Let's go way over here. X is equal to 0.5 now. Y is equal to something. It's the same process as normal. It's the previous x and y. So in this case, we're looking at the line above. The previous x is 1. The previous y is 13/2. So it's going to be 13/2. Again, because the step size is negative, it's going to be minus 1/2. And then what we're going to do is we're going to plug in the previous x, which is 1. So it's going to be 2 times 1. Minus the previous y, which is 13/2. So it's going to be 2 minus 13/2. And we're going to try to compute this. So this doesn't look too bad because these 2's cancel. So 2 minus 13 is negative 11. So it looks like we have 13 halves, but be careful with negatives just like normal. Negative 1/2 times, what did we say it was? It was 2 minus 13, which is negative 11. So it's going to be 2 times plus 11 halves, I think. I don't know why I'm struggling here. It's 24 halves, which is going to be 12. Again, all you're doing is you're doing a little bit of fraction work. 2 minus 13, I believe, is negative 11. Then negative 11 times this negative 1/2. You're canceling out the negatives, so it's plus 11 halves. You add the initial. But again, it's the same thing. It's the previous y, which is 13 halves, minus 1/2, which is plus the step size, and then plugging in the old x and the old y into this formula. Unfortunately, we have to do it one more time, so it's going to be x is equal to 0. But it's still the same formula. It's the previous y, which in this case was just the nice number of 12. Then we write minus 1/2. And then what we're going to do is we're going to plug in the old x and the old y into our slope. What's the old x? Well, it's 1/2. So it's going to be 2 times 1/2. What's the old y? That's 12. So it looks like we're almost done. It's going to be 12 minus 1/2. Let's simplify this parenthesis. It's going to be 1 minus 24. That's negative 23. So it looks like our final answer is, well, 12 is 24 halves, so it's going to be 24 plus 23 halves, because it's minus minus again, so it's going to be 47 halves is our final answer. So in this case, we have the rare case where you have to employ Euler's method 3 times, but that's because we started at 1.5 and we went to 0. Just a few things to keep in mind. The first thing, by far the most important thing, is just knowing the formula. Previous y plus step size, plug in previous x and y into your differential equation and just solve that thing. The next and most important thing is how to go from step to step. When I say previous x and y, you look at the line immediately above it. Another thing to keep in mind is just try to do Euler's method the correct number of times. Start off at the number you want, or the number that you're given actually, and then you move the step size until you hit the number you want. So that's why I like that I write at 1.5 and 4, not only because it's previous x and y, but I can just visibly see, oh, I need to do it one time to get to 1, one time to get to 0.5, one time to get to 0. And then keep in mind that for this one, the small thing was that h was negative because we're trying to approximate a y value for an x value that's less than our given x value. But hopefully you see that in the last 3 questions, all of these questions were the same, which is employing this formula over and over and over again. Previous y plus step size, plug in previous x and y into your slope. And that's all it is, where everything is given for you, so all you have to do is just be careful with fractions and just find your answers. But what I'm going to do is I'm going to do a multiple choice question to end this video that's really similar to this process, but might even be easier because you're not going to actually have to find slope because it's going to be given. So let's do that. One more question, a nice little table. So I'm going to erase this. We're going to erase this guy. And what we're going to do is we're going to, again, use 3 equal step sizes. But we're not going to have this. So this is Euler's method with a table. And the given value that we're going to start off with, let's say our given value is going to be 2, 6. And what's going to happen is we're going to have this nice, beautiful little table. Hopefully I can draw a good table. So this is also a given, x. And we're going to have f prime of x. Then we're going to have 2, 4, and 6. And then finally, let's do 8 here. And we're going to have random numbers here. Let's have negative 1, 3, 4, and I don't know, 2. So this is my nice little table. And the question is, again, approximate f of, let's say, 8. Where f of x, of course, is equal to y. And f of x has f prime values that are given in this table. So again, it's not going to be any different than our previous one. So let's just start off with a process where when we find slope, we're just going to use this table instead of using a given differential equation. So in this case, it's going to be x is equal to 2, y is equal to 6, just like normal, writing out our initial point. We have 3 step sizes, so we do have to determine the h in this case. But notice that because we have 3 step sizes and we want to go from 2 to 8, it looks like our h is just going to be 2. because we want to go 2, then 2, then 2. So h in this case is not going to be a fraction, which I'm not going to complain about. It's going to be 2. So let's go for this process. What's the next y? Well, the next y, we can't go from 2 to 8 immediately. We have to add our step size, which is 2. So we have to start at 4 first. But it's still the same process. It's the previous y, which is 6, plus the step size, which is 2 in this case. Then we're going to plug in our old x and our old y into our slope. But keep in mind that it's just given in this table. So if you plug in the old x, you don't even need the old y actually. You're just plugging in this old x. What's the slope here? It's just going to be negative 1. So it's going to be 2 times negative 1. Because again, you plug in those old x and y into your table or your differential equation. There was no y given. It's just x, so it's negative 1. So in this case, it looks like our answer is going to be 4. Then we have to do the process again. So it's going to be x is equal to 6 now. So the formula is previous y, so it's going to be 4 plus the step size. So this is consistent with the previous line because the step size doesn't change. Plus 2, plus 2, plus 2, 3 equal step sizes. That should be more precise. So then we're going to plug in our previous x and y, the line immediately above it, into our table. Looks like our slope is going to be 3 here, so it's going to be 2 times 3. So in this case, it's 4 plus 6, which is 10. Again, using previous x's and previous y's. Finally, we have x is equal to 8. So let me write a better 8 because this is the last part of the video. So it's going to be y is equal to previous y. So in this case, it's 10. Always looking at the line immediately above it. Step size doesn't change, so it's going to be plus 2. And then what you do is you find the slope at this previous x value. It's going to be times 4. So it looks like our final answer is 10 plus 8, which is 18. Keeping in mind that we never use this slope value because that would be used if we wanted to find x of 10, for example. But Euler's method is always the same, no matter how the information is presented. Previous y plus step size, plug in your old x and your old y, usually in a differential equation, but potentially in this table. But hopefully you see that after this video, as long as you know the formula, as long as you can add and multiply fractions, you will be very confident as you answer these Euler method questions. They can't really trick you with Euler's method question. There's no crazy hard variation of Euler's method. They're just slight variations where you might do it more times, or the step size might be negative. There might be a little bit more fractions. The slope might only depend on x or y, but it doesn't really matter as long as you just know where to plug things in. But of course, if you want more practice with this, that's certainly valid. So in the description of this video, I'm going to link our Girls Teach Calculus video where one of my former students practices several Euler's method questions, sometimes 2 steps, sometimes 3 steps, depending on the question, sometimes with fractions, sometimes with negative step sizes. So be on the lookout for that. But thanks again for watching this video as we continue our differential equation coverage on the AP exam. We highly thank you for watching our videos, liking and subscribing and things like that. Hopefully I'll see you next time. Thanks again for watching.